Welcome to the first part of the problem-solving session for Chapter 28. Let's begin with the first question. Here, we're told a car battery has an EMF of 12 volts and an internal resistance of 0.05 ohms. The terminals of this battery are connected to a load or external resistance of 3 ohms. And we're asked to determine the following: the current in the circuit and the terminal voltage. Well, let's see. Let's raise this up just a little bit, extend the page so we have a little more space to write. To get the current in the circuit, we use Ohm's law. I equals delta V over R, except that we don't know what delta V is equal to. In fact, delta V is going to be equal to IR, and if we divide that by R, we get nowhere. So what we're going to do is we're going to make use of the relationship that we derived earlier, where we know that the EMF will be equal to delta V, or IR, I times the load resistance, plus I times little r, the internal resistance. This is our delta V. And in this expression here, if we factor out the current, we get I equals EMF divided by load resistance R plus little r, the internal resistance. And by the way, we can write the EMF as just E or EMF, whichever is your preference. Well, we know the EMF is 12 volts and the load resistance plus internal is 3.05 ohms, and that gives us a current through the circuit which is equal to 3.93 amps. Now, in fact, we can solve for the output voltage or the terminal voltage using Ohm's law. Delta V equals IR. We have our I, 3.93 amps. We have our R, 3 ohms, and my calculator gives me a voltage of 11.2 volts as our terminal voltage. Next, in part B, we're asked to determine the power which is consumed by the load resistance or delivered to the load resistance. Well, we're going to make use of the delta V that we just found, because after all, this is the output voltage. This is what is actually supplied to the load resistance. Square that, divide by the load resistance, and we get 46.4 watts delivered to the load resistance, or dissipated in the load resistance. How about what is dissipated or lost to internal resistance? Well, here we can take the current through the circuit, square that, and multiply this time by the internal resistance. So 3.93 amps squared multiplied by 0.05 ohms gives us a power loss to internal resistance of 0.772 watts. In the last part, we're told that the internal resistance has gone up now to 2 ohms, possibly over the continual use of this battery. And now we're asked to compare the power which is lost to internal resistance. Well, in order to do this, we must first find the current that will flow through the circuit when the internal resistance has increased. We use the same expression EMF is 12 volts, but this time we add the load resistance to 2 ohms, giving us a total resistance of 5 ohms, and that now reduces the current to a value of 2.4 amps through the circuit. Well, the power that is now going to be lost will be the current. Notice I'm using the primes here just to differentiate the current or the load resistance and the power after the internal resistance has increased. Well, when we now take 2.4 amps squared multiplied by the internal resistance, we get a value of 17.3 watts, which are now lost to internal resistance in the circuit. Next question. Here in question 2, we're told to consider these 3 resistors, R1, R2, and R3, which are identical and have a value of 2 ohms. These are connected to a 6-volt battery. In the first case, we're told that the switch is opened and we're asked to determine current, voltage drop, and power through each bulb. In the second case, we're told that the switch is closed and we're asked to determine all of these quantities again. Now, what we have to note is that when the switch is closed, we now have a junction point in our circuit, which means that when the current has flowed past R1 and R2, it encounters 2 paths, one of which has no resistance, or is the path of least resistance, as we might say, the other with a considerable resistance, R3. Well, you can see that what will happen is that the current will choose the path of least resistance, and so in this case we say that resistor 3 has been shorted out. But first, let's consider the open switch case. Here we've got, first of all, a connection that is in series, and so our total will be the sum of the individual resistances, R1 plus R2 plus R3, giving us a total of 6 ohms. Well, because they are also in series, it will be true that I total equals I1 equals I2 equals I3. And so if we're looking for the individual currents, we find first I total, which we can determine from Ohm's law, delta V total divided by R total. Delta V total is 6 volts, R total 6 ohms, therefore 1 amp of current will flow through the circuit. The potential across each of these will be given by Ohm's law as well. Delta V1 is the product of I1 times R1. Well, I1 is 1 amp, R1 is 2 ohms. Therefore, delta V1 is equal to 2 volts. However, because the same current flows through each resistor and the value of the resistance is the same, delta V2 will equal delta V1 equal delta V3, and therefore 2 volts will be the potential drop across each resistor. How about the power? P1, we can use the expression delta V1 squared over R1, which is equal to 2 volts squared divided by 2 ohms, 2 watt, and for the same reason that delta V is the same for each resistor and the R is the same, this will also equal P2 and this will also equal P3. Notice that P total is the sum of the individual powers and should be 6 watts. Well, now let's take the case where the switch is closed. In this situation here, as we said earlier, R3 will be shorted out, and therefore I total will simply be equal to I1 and I2. R total will be simply the sum of R1 plus R2, which will equal 4 ohms. I total is delta V total over R total, which is 6 volts over 4 ohms, gives us 1.5 amps. And so now you can see the current is greater through each resistor because we now only have 2 resistors to consider. How about delta V? Well, delta V1 is given by, let's just extend the page a little bit. I1 times R1, I1 is 1.5 amps, R1 is 2 ohms, that gives us 3 volts, but that will also equal delta V2. P1 equals delta V1 squared over R1, which is 3 volts square over 2 ohms gives us 4.5 watt, which is also equal to P2. And P total, which is delta V total over R total, is equal to P1 plus P2. In other words, 9 watts. Next question. Here we are given 4 resistors in a combination of series and parallel. We are told that there is a potential difference, in other words, a battery, that supplies 42 volts across A and C. So in other words, we've got a 42 volt battery between the points A and C. We are asked to find the total resistance, the current through each resistor, and the potential drop across each resistor. Let's proceed. The first thing we want to do is to look for or recognize arrangements of parallel or series for our resistors. If we come up here, we can see that resistor R1 and resistor R2 are connected in parallel. We can also see that resistor R4 and R3 are connected in series. But if we first combine our 2 resistors in parallel, not only is R4 and R3 going to be connected in series, but the combination of 1 and 2, R12 we call it, is also connected in series with R4 and R3. And so that'll be our game plan. We will, here's our point A. Let's go ahead and just redraw how we are going to connect up, this will be the point B, our circuit, so that we can systematically reduce it to a series circuit and therefore collapse that, combine that into one equivalent resistance. So our game plan will be to first combine R1 and R2 so that we have an equivalent R12, and then combine those 3 series circuits so that we have an A, a C, and then R, 1, 2, 3, 4. So let's begin with, and I'll just extend my page here, R12. 1 over R12 is equal to 1 over R1, in other words, 1 over 6 ohms, plus 1 over R2, 1 over 3 ohms. We find a common denominator, 6 ohms, and we get 1 plus 2, excuse me, 3 over 6 ohms, And if we take the reciprocal of that, we get R12 is equal to 2 ohms. Now, we can go to the next step, which is our series connection. R1234 is R4 plus R3 plus R12. In other words, 8 ohms plus 4 ohms plus 3 ohms. Excuse me, 2 ohms, what we just obtained above. And that gives us an R total, which is 14 ohms. Next, we're asked to determine not only the current through each, but also the potential difference across each. And the way we're going to do this is in a combination of working with currents as well as voltages, so that when we reach a point where we cannot determine a quantity, we can systematically move on to the other quantity to ultimately end up with a solution for all quantities. Now, recall that R12 with R3 and R4 were connected in series. And what that means is that I4 will equal I3 will equal I12, which will equal I total. So how about if we get I total using Ohm's law? Ohm's law says that I total equals delta V total divided by R total. In other words, 42 volts divided by 14 ohms, and that gives us 3 amps. So therefore we can say I4 equals 3 amps, I3 equals 3 amps, and I12 equals 3 amps. Now, notice that I12 is the sum of I1 plus I2, since R1 and R2 were in parallel. So we don't know what I1 is or what I2 is, we just know the sum. This is when we stop and we decide to solve for the quantity delta V4, where delta V4 using Ohm's law is I4 times R4. Well, that's 3 amps times 8 ohms, which is equal to 24 volts. Delta V3 is I3 times R3, or 3 amps times 4 ohms, that's 12 volts. And delta V12 is equal to I12, which is 3 amps, times R12, which is 2 ohms, and that's 6 volts. However, delta V12 equals delta V1 equals delta V2, since those two resistors are in parallel. Well, that has just allowed us the ability to get individually I1 and I2, because I1 is equal to delta V1 over R1. Since we now know delta V1 is 6 volts, divide that by R1, 6 ohms, we get 1 amp. For I1, we'd repeat and do the same for I2, either through Ohm's law or by noting that the sum I1 with I2 is 3 amps, and if I1 is 1 amps, therefore I2 must be 2 amps. And now we have solved all of the unknowns in our circuit, and that will always be our strategy, to work with what we know first, and when we reach a stopping point, to then move on to the next quantities that we can determine. And always we try to make use of Ohm's law to help us work through the unknown numbers. Next question. Here we are given a connection of 5 resistors with a battery and we're asked to find the total resistance as well as the potential difference between the points A and B. Now, I had to remove the drawing here, which you see as blank, because it did not translate very well. So let me see if I can go ahead and reproduce this circuit for you so you can see one other viewpoint, one other way of looking at the same circuit. We take the circuit and we rotate it counterclockwise so that our battery, 25 volts, is here. Our resistance R1 is here. Here we have the points B. Here we have the points A. Next, you can see that R2 is this resistance here. So let me go ahead and just label R1, R2. And parallel with that is R3. Let's label that. And parallel with that is the combination of R4 and R5. Let's label that R4, R5. So our strategy for getting our total will be to try to reduce this circuit so that we can ultimately combine it to get an R total. Now, if you notice here, we try to work furthest from the battery towards, and you can clearly see that R4 and R5 are in series with each other. So let me go ahead and see if I can work out the steps for you so you can see the diagram as we begin collapsing our circuit, reducing it down so that ultimately we'll only have one resistance. We have our R1 here. We have our R2 here. We have our R3 here. And the combination of R4 and R5 will give us an R45. Now, of course, R45 is the sum of R4 and R5 because these resistors are in series. So R45 is equal to 20 plus 5, or 25 ohms. Now, when you look at the circuit, what we have left over, R45, R3, and R2 are in parallel with each other, since the same potential difference across each is what is across, in fact, the points A and B, which is where we'll want to go next. All right, well, we have 1 over R, 1, 2, 3, 4, pardon me, 2, 3, 4, 5, right? Let's get our eraser and clean this up a little bit, since we are not involving R1. R2, 3, 4, 5 equals 1 over R2, which is 1 over 10, plus, oh, let's put our unit, 1 over R3, which is, oops, we've had a screen that suddenly come up, and we can't seem to get our cursor to reduce this down. Ooh. Oh, seems like our